most well known in our industry, I guess, for fiber and cable testing. But we also have an optical division. Just a very brief overview of the heritage from the Viavi side. It started as Wandel and Golterman. I think back to those days, it was a similar time when companies like Marconi were starting. That became JDSU, and moving forward, morphed and evolved into what we now know as Viavi. If we look at it just purely from the Avcom side, so from our division, you see some very rich heritage here. You see Marconi instruments, you see IFR, Aeroflex, Cobham, Wandel and Golterman, and probably the one that's missing on here is Wiltec, which interestingly was actually something that fell out of Wandel and Golterman originally in the JDSU Acturna days, and that was actually purchased by Aeroflex. So that's a lot of heritage in terms of radio test set. You know, Marconi, IFR, Aeroflex, and Wiltec were all making radio test sets, and that's all merged into the Avcom group now under Viavi. Viavi likes to be number one in the market segments that it plays in. So key elements of the test and measurement field, wireless and avionics. We're one of the leaders of 5G technology. Avionics for both commercial and military applications. And then the other division we have, which is optical, is number one in its market, for example, for anti-counterfeiting ink. So there's over 100 countries around the world that use our ink for their banknotes because of its capabilities for anti-counterfeiting. It's also used on security seals on a lot of the game machines, which are high value computer products. So today, like I said, we have 3 test sets. I'm going to focus on the 3920B, but I will touch on the 8800 a little bit. And for those that know, the 3550 is a smaller, more portable unit that has many of the features of the 8800. So there'll be a very quick recap on why you should be using these modern, inverted commas, digital radio test sets. By digital, we mean they support digital radio technologies such as DMR, TETRA, P25, NXDN. Of course, they also support analog, so things like AM and FM technology. We'll touch on the key differences between the DMR and TETRA physical layers. You know, we're not looking to test all the software in the radio. We're not looking to test the whole protocol stack and messaging inside the radio. We're looking to test really the RF and audio capabilities and whether they are good or bad in each of those radios. Then we'll look at actual testing. So I'm going to start with DMR transmitter tests and then switch to TETRA. And then I'll come back to DMR with receiver tests and again switch to TETRA for receiver tests. We'll finish up with a 1-slide summary, and then we'll open up for a question and answer session. So why is it essential to use a modern digital radio? I think, you know, before I put the rest of the slide up, if you look at the bottom, the picture with the blue background, we see 4 lines, which if this radio was very well tuned, very well calibrated, you would see 4 very straight lines on those vertical dotted lines. What you see here would be or could be typical of a radio that has been tuned on an analog radio test set. And this is in fact a screenshot from one of the manufacturer's radios before they were using the modern digital test sets. They were tuning them with analog test sets, and the analog modulation was fine, but they were corrupting the digital capability. What does that mean? It means a loss of coverage or loss of range in your radio system. So it doesn't matter if your power is on full power, you will still lose range and coverage. So analog and digital systems, we have to do a frequency measurement. We want to check that the radio is on frequency, so we're looking for frequency error. We're going to check the transmitted power is good. If it's too high, it could be illegal because you have a license for a particular power level. If it's too low, you can be affecting the link budget and therefore the range of your radio system. And remember, when you think of the range of the radio system, you've got to think at the radios at both ends. Could be two portables in walkie-talkie mode. It could be a base station at a cell tower, and it could be, a mobile in a vehicle. So always consider both radios on the two ends. There are two transmitters in the system, not one, and they both have to have good performance, or you compromise your system. And for analog, we have modulation. Typically, it's AM or FM. Occasionally, you'll see phase modulation or single sideband, but typically AM or FM. And this is where we deviate now, because for digital, we don't have those analog modulations anymore. So we start looking at digital parameters. Okay. So sensitivity, again, on analog radio, we're going to look at things like synad measurements or SNR measurements. Whereas on digital, because we're now transmitting effectively a bit stream over wireless, we're going to be looking at bit error rate or message error rate. And here's some of the other digital measurements we need to make. So how good is the quality of the modulation? The FSK error or modulation fidelity. How good is the symbol timing clock? Remember, this is a digital system, and if the timing clock is wrong, that will cause bit error rates. We may have a TDMA structure where we have multiple radios transmitting on the same frequency, and they take turns to transmit in their slot. I do apologize why that's jumped back out. So we may need to look at the slot power and the slot timing, and also the magnitude error. So this is the error in the amplitude of the signal. For example, it should remain constant on DMR, but if it's varying over time, we need to measure that magnitude error. In terms of the differences between DMR and TETRA, they are very, very different modulation types. Okay, so DMR is using a 4-level FSK modulation system, and this is similar to other technologies such as P25, NXDN, DPMR, for example. So any of those technologies, when we talk about DMR today, they are broadly similar in terms of the measurements we can do and the graphics that you would see. Okay. TETRA, by contrast, is a different modulation. TETRA is using what's called pi/4 differential QPSK. So whereas DMR is using effectively a digital version of FM, for TETRA, we're actually using a digital version that implements amplitude and phase, not FM. DMR as a system has 2 time slots. It's a TDMA system, so we have 2 users on a channel, for example. Whereas TETRA, we have 4 users on a channel. Now, interestingly, DMR has half the channel bandwidth of the TETRA system. So if you consider the effective bandwidth per user, for DMR, you see 2 users share 12.5 kilohertz, so the effective bandwidth per user is 6.25 kilohertz. And if you look at TETRA, we have 4 time slots and the 25 kilohertz bandwidth. So almost exactly the same, we have 6.25 kilohertz bandwidth per user in terms of effective bandwidth. So when you look at some of these modern digital systems, they actually use effectively the same bandwidth per user. Now, these radio systems also use a codec. So this codec basically takes the human voice and converts it to a digital bit stream. And then at the other end, at the receiver, it will then decode it back from a digital bit stream to an audio signal. So along with this, of course, we have error correction. We have control bits interspersed within that digital bit stream, and the system has to code that correctly and decode it. But you'll notice that different codecs were developed or designed for the different radio systems. There are arguments over which one is best, but at the time each of these were developed, they were the best that were chosen for that particular technology. For both DMR and TETRA, we actually transmit 2 binary data bits per symbol, and the symbol is basically, a small cluster of bits, of digital bits, As I say, in this case, it's 2 bits per symbol. So when we transmit a signal, we transmit a symbol. So we transmit 2 bits of data at a time. If we just do some very quick comparisons, if you look at GSM as a classic digital phone technology, the first one we had, I guess, for Europe, effectively there were the 8 users in a 200 kilohertz channel. And if you compare that to analog, it was very similar, 8 users in 200 kilohertz channel. But nowadays, with these digital technologies such as DMR and TETRA, we have quadrupled that. So we now have 32 users in an effective 200 kilohertz channel space. Okay, that would be multiple channels with multiple users. But you can see how technology has progressed, where we can take the human voice and data, we can compress it, just like you would compress using WinZip on a Windows document or file. We can compress the data, we can do some clever things to recover that data at the end, or that voice, and bring it back at high fidelity. I mentioned near the start that DMR was a sort of digital FM based system, and TETRA was based around analog and phase. And if you actually look at the blue equation, the more complex one, you'll see for any signal that any person can ever create, there are only 3 parameters over time, and that's amplitude, frequency, and phase. Okay, so with analog, AM modulated the A over time component. For FM, we modulated the F over time component. Whereas for digital, we can modulate just one of those, for example, the frequency, if it's DMR, or we could modulate 2 or more. So for TETRA, we modulate both amplitude and phase. Okay. So just remember, there are only 3 physical dimensions that we can manipulate for any radio system known to the universe. This shows 2 pictures, basically. If you look at the bottom left picture, you see 4 points. As I said, if this was a very well-tuned radio, you would see the radio transmitting, and this is real, this one. It's a very good radio, and it's transmitting effectively very clean lines almost on those 4 vertical dotted lines. So that would be a very, very good DMR transmission. On the right, just to show you mathematically here, I'll show you a real picture in a moment, shows a TETRA picture. So on the left one, we're really showing frequency as you go left and right. And on the one on the right, we're showing more like an XY graph. So as you go in and out from the center, as you go further from the center, you're increasing the amplitude. And as you go around the circle, you're changing the phase. So we can represent both amplitude and phase on this picture. Okay. So now you see what the TETRA picture looks more like on a real radio test set. So in both cases, we've got to measure the frequency error, just like we did with analog. We've got to measure the slot power. So this may be, this is bursted power, not necessarily constant power, depending what radio systems we're using. And then we've got to consider some other issues with the power. So for DMR, the radios typically will be programmed for a low power and a high power. Okay, it depends how the user wants to program them, but quite often you'll have low power and high power. So if you're in short range communications, you would use low power to conserve battery and talk time. But if you're in a longer range, or you're having trouble receiving or sending messages, you may switch to high power if that's programmed into your radio. TETRA is different. TETRA uses a number of power steps, and these are 5 dB steps. So you don't have low power and high power. You could have 6 or 7 or 8 power steps, which typically you do not control. The system controls that for you, and I'll explain that later. We need to look at the symbol clock error or timing error in the system. Again, what we're doing is when these signals are running, there is effectively a data clock running inside the unit. Typically, 4,800 symbols per second, 9,600 bits per second, 2,400 symbols per second, those sort of data rates. But that timing clock is when we actually take a measurement of where the frequency or the amplitude and phase are at that instant in time and make our decision to decode our binary data. So those clocks have to be accurate, or we have problems with decoding the data, and that will compromise our system. We've then got to look at the modulation quality. So for DMR, one measurement. I do apologize why it keeps jumping back there. We've got to look at the modulation quality. So for example, for DMR, we'd look at symbol deviation. For TETRA, we'd look at EVM. Again, another one. For DMR, we could look at FSK error. And you'll see for TETRA now, we have two measurements, error vector magnitude. So you'll see in a little while on the picture there, what we actually do on the radio test set is we look at those bright points. There's sort of 8 bright points around the circle. And that is where we do the measurement of the quality of the modulation. That is our timing points. And the same with the DMR, for the FSK error, the timing points are at these 4 frequency points you see on the graph. They're the ideal positions. Okay. For DMR, we may look at magnitude error, which again is the changing amplitude over the burst, the power burst, because due to nonlinearities, any magnitude error can translate into affecting the frequency. You get AM to PM conversion, which could impact the frequency. On TETRA, what might be important is we look at carrier leak. So this is unmodulated carrier breaking through onto the output. So if there's poor screening on the radio, or a poor track layout on the printed circuit board, so signals are coupling across tracks on the board, you can see things like carrier leak, and again that will compromise the quality of the transmission and what you can receive. So for DMR, if we look at the 3920B, which is the big picture on the bottom right, we have 4 measurement windows available. So we can set those 4 windows to effectively anything we want. And I give you some examples of the measurements we can select. Just a little picture on the top right, the 8800 on there. Typically you would have 2 measurement windows, but you can move them around, you can stack them on top of each other. You can make them full screen or normal size. But generally in these cases, any of these windows on either product, or including the 3550, the 3 products, any of these windows you can either maximize to full screen or make them small again. You cannot physically resize them as you would on a Windows computer, for example. Okay, it's a small window or full screen window. So I've said you can choose those measurement windows. So you might choose unit under test measurements. And if you look on that measurement window on the lower picture, you'll see I have 6 measurements on there. Within that window, I can choose which 6 measurements I want to show. There is in fact nothing to stop me making more than one of those windows UUT measurements. I could have 2 windows. And they could have exactly the same measurements, but one could measure average and one could maybe measure maximum or worst case. Or I could have one UUT measurement window measuring what you see here, and the second window measuring 6 different parameters. So it is very flexible what you want to show on the radio test set. We might want to decode the color code, call ID, etc. This actually is quite useful. We've done this, for example, in the US at American football games, where people used to program radios onto the same frequencies as the referees were using, and then they could broadcast some crazy messages on the PA system in the stadium. Well, then the organizers decided, great, we'll use digital radios. They didn't use any encryption. So then the guys in the stadiums, they realized this. They brought some DMR radios and they started broadcasting on the PA announcement system in the stadium again. So we were actually decoding their transmissions and their radio ID and call ID, and broadcasting privately back to them that, you know, the police are coming, you better turn your radio off. So you can see real applications where the decode can be very useful above and beyond checking your own radio. We might want to do advanced analysis, so this allows us to show both the FSK error, the 4 frequency points, and the magnitude error. Okay, so we're doing 2 measurements in one. We might want to look at the modulation. So on that lower picture on the bottom right distribution plot, you can see the 4 frequency points where we do our timing measurements and decode our digital data. We can represent that in 2 other ways, either as a constellation diagram, so you see 4 little circles, as if you're looking from above, from the sky, looking down on those 4 points, or we can show it as an eye diagram, which is more, shall we say, conversant with engineers who have maybe come from a telecoms background. And then for power, we may want to look at the full power burst profile. We might want to look just at the ramp up and ramp down segments, or we might want to look at the power over time. So now over multiple bursts, to see if the output is, shall we say, drooping. You get amplifier droop. As the amplifier gets hotter, quite often you'll actually see the power output will drop a little bit due to that heating of the amplifier. It will lose some gain. Now remember, I said for DMR, the radios typically have 2 power settings. So if I'm measuring the low power and it's set to 1.2 watts, you can see here my signal power is green. On both plots it says 1.2 watts. If I switch to high power on the radio, it will go red, may say 5 watts, and fail. So just bear that in mind, that the power level you're testing, that you have the correct color-coded pass-fail limits if you're using the colors on the radio test set. Now, the other thing I want to show you here is do not rely on the broadband power meter in the radio test set. Because the signal is bursting on and off, if you look at the plot on the left, you'll see the broadband power is just over 1 milliwatt. It is grayed out. It's not real, it's just noise. And on the right-hand plot, it's about the same as the signal power. So on the left, we've done a sample of the broadband power when the burst was off, and on the right-hand plot, same thing. We've done a measurement of the bursted power when it's on. Okay, but what you'll notice is you may get other power levels in between as we catch it and do a sample measurement on the ramp up or ramp down. So I never use the broadband power meter as an accurate power meter for these types of measurements. And even if you think, oh, I've got a modern broadband power meter, you could have a bird power meter, for example. You might set that to a 50% duty cycle. Well, I'm on for one slot and I'm off for one slot, so it's 50%. So you set it for 50%. Again, you get an inaccurate power measurement because the power ramps do not suddenly come on and come off at the start and end of your burst. If they did that, they would cause a lot of spectral problems. So you have to be very careful doing power measurements. Always use the in-channel power meter. Okay, so it's either signal power or the slot 1 power is what you would measure. It's exactly the same reading. Okay, and you'll see because we've got the color coding in green, you can actually key a radio very quickly if you're in the field and you just want to do a very quick radio check. You can key the radio, everything goes green. You then dekey the radio, listen for a 1 kilohertz tone at sensitivity level. Your radio is functioning well, okay, on that channel. So if you're literally about to go into an operation, you could be a National Crime Agency, FBI, or an equivalent in Europe. You may want to actually do a radio check before your guys deploy into that situation. And in fact, that's what some of the high-end police organizations and anti-crime organizations will do. They will actually check the radios each and every time they go on an operation. So again, remember what I said, what a bad radio looks like and why is it important? Okay, the radio could be under deviating. And this is classic when you're using an analog test set. The analog test set, you're actually tuning the digital radio using analog FM. And the problem with the analog meters, the FM deviation reading you get is a peak reading. So if you have noise or other errors in the system, then that will be included in the measurement. So actually, you think the reading is high, you tune the radio down, and it actually then under deviates in digital mode. Okay. The digital test sets don't have that problem. You can also over deviate. Again, people use the wrong analog filters, or they don't use any filters, and then the reading you get is low in FM mode, so you actually tune it up. So then when you go to digital mode, you're now over deviating. The points can be noisy, and they're noisy because of one or two of the above that I've mentioned. It could be the timing error, could be other jitter, and it could be because we're not doing it at 1 kilohertz, we're now doing it at 2 different points, maybe 150 hertz audio tone and maybe 3 kilohertz. If those two tones are not flat, absolutely flat relative to each other on the FM deviation meter, that will cause a serious impact as well. And one of the manufacturers, for example, they specify flatness of those tones across the audio band 0.05 dBs. And so, you know, as new as we can say, perfectly flat audio response. You do not get that from the old analog test sets. They were only ever designed to let you listen to audio and to tune at 1 kilohertz. And frequency error as well is a problem. So again, you can't measure this on the analog test set, you get the wrong answer. You have to digital process it to get the correct frequency error for these radios. Okay. And then power is another issue. If your power's wrong, you corrupt your link budget and your radio range. But remember, these noisy signals, and this is what you're transmitting, these will seriously impact your range as well. Just as if you've chopped the power in half, or by 20-30%. So you do need to tune these radios correctly. They are tuned using FM and CW, but you cannot do it using those analog test sets if you want a good quality tuning on the radio. Okay, so move on to TETRA, and I'll show you a couple of little videos in a moment. For TETRA, it's more interesting because with DMR, if you're on an open channel, you can just key the radio and we can start demodulating. We don't care if we're on the right frequency. We don't care your color code, your radio ID, your call ID. We will just take any of those, tell you what they are, and show you the transmitter measurements. With TETRA mobiles and portables, it's more difficult because you need the radio to register onto the network. If it's typically on a trunk network, then we have to set a number of parameters first. So we've got to make sure we're on the right frequency plan, we're on the correct control channel that the radio is looking for, we have the correct country code and the correct network code. If any of those are wrong, the radio will not register and we cannot get it to transmit. Okay, and then you see on the bottom right picture, there are some other parameters called access parameters, which typically we don't touch, but you'll see in a moment how we might use those in the measurements. So in terms of the transmitter test, you now see the screens on the 3920 look a little bit different. Okay, so at the top we still have RF settings showing the frequencies and the power level, but at the bottom we now have an operation status window. That's showing us what the radio is doing in terms of if it's in a call, if it's waiting, if it's receiving text messages, or if it's making a call to the test set. And remember, the radio has no idea that the test set is a test set. It believes the test set is actually a base station. So it's behaving as if it's in the real environment. You'll see two measurements here. Okay, we're showing all the transmitter measurements, or some of the transmitter measurements in green, and we're showing a constellation picture, what I call a rotated vector, on the right-hand side, and I'll come back to that. The easiest thing to get these measurements is just key the radio. So once it's registered on the base station, the test set, you key the radio and it will start doing measurements. Okay. The measurements by default are color coded for pass or fail. Blue is fail low, red is fail high, green is pass. And by default, we use the ETSI predefined test limits. and we have normal limits and extreme limits. Okay, so typically normal limits are used, extreme for high temperature user applications. And here's an example of some of the measurements, or most of the measurements that we can do. Okay. We can make different types of calls from the test set base station to the radio. Equally, the radio can make those same different types of calls to us. I tend to use a phone call for demonstrations because once I have it in a call, I don't have to press the push to talk button. Okay. You can do group calls, you can do private calls. I would recommend you do not ever make or test by doing an emergency call from the radio to the test set. I've been in numerous situations and heard of situations where people have pressed the red emergency button because they want to check that's working, of course. And if you're near a base station, so like you're in a police headquarters, there's usually a base station nearby. Sometimes that signal is so strong the radio will jump back onto the live network. Now when you press that red button, you know, lots of people start running around. So I always recommend do not make an emergency call from the radio to the test set in case it has jumped back to the live network. If it's a test radio, no problem. And the test set making an emergency call to the radio itself, again, no problem. Just don't do it from the radio back. Okay. So just to give you a little idea of what this looks like. So when we're actually testing the radio, I've now set the radio up. So it's in a, apologize again. So it's in a call now, it's in a phone call, so I'm not having to press the push to talk button. I can look at different types of bursts. I can look at statistics. So I've set everything to average rather than maximum or worst case. And then when I go and minimize the screen again, you'll see all those measurements now say average. On the right, I show a constellation. Okay, I can show power. So I may be interested in the ramp up and ramp down. See, there's a little notch on the ramp up, and then it's fairly smooth. So this is one manufacturer of radio. You'll see in a minute a different manufacturer of radio and how their ramps look considerably different. Okay, so now I'm just showing you a few different measurements. So trajectory on the right. On the left, I've taken those 8 constellation points and mapped them onto one. If I look at the protocol, this tells me what's been happening with the radio. So, you know, I've registered the radio. I may have then done a commanded registration. I put it into different calls. I can get it to produce a 1 kilohertz test tone out of the radio. I can make it go silent. I can talk into the radio, and that voice will then come back out of the speaker. So I have a voice loop back as well. So that's just an example of some of the measurements we can do on the TETRA mobiles and portables. Okay. So not going into too much detail on direct mode and base stations, but we can get broadly similar measurements. Now, what you'll see on the right-hand picture here is quite interesting because this is another manufacturer. And now if you look at the ramp up, you'll see there's a big spike and then it comes down again, then it ramps up very quickly. If you can see my mouse, it ramps up very quickly close to this edge. And this line is the limit. It has to be at full power by the time it gets to this point in time. Okay, then we have the power burst. But because it ramps up very quickly, that causes spectral spreading or spectral interference, but it maintains itself within the limit of that spectral mask. It maintains itself within the power rising, you know, time limit here. But you actually start to see some features here as well. So on the actual vector, rather than being a slightly noisy dot in the middle of those 8 points, you'll see the amplitude has been compromised, maybe it's the wrong word, but you see the amplitude has been impacted here. But it's still within specification. So what this manufacturer has done is they've ramped the signal up as quickly as they can and as close to that timing edge as they can to try and conserve battery power in this ramp period. And the starting and the end ramp points are both together about between 5 and 10% of the time. So if you can save 5 or 10% of battery, that gives you maybe an extra hour of talk time. So you see why people might want to do this, and they've been very clever. That ramp is so close, they just keep the constellation so that the error vector magnitude measurements in spec, and they just keep the spectrum measurements in specification to manage to do that battery conservation. Okay, so different manufacturers approach that in different ways. For TETRA, unlike DMR, where we're keying the radio and we have low and high power, for TETRA, the radio helps the network. So basically what it does, it says, okay, I've got this access parameter, minus 45 in this case, which the base station or the test set has broadcast to me as one of the control parameters. If I receive a signal, say at minus 60 dBm, I will transmit minus 45 minus 60, that's plus 60, that's plus 15 dBm. So it will transmit a signal at plus 15 dBm. If I receive a signal at 70, minus 70 dBm, minus 45 minus 70, so that's plus 25 dBm. So you see the power level changes based on the signal strength that it receives. There are some rules to that. It can't go below plus 15 dBm. It can't go above the radio's power output capability. So if it's a 3-watt radio, it obviously can't go above 3 watts. Or again, if you look in the specification on the test set, we've done max TX level 30 dBm or 1 watt. So even if I had a 10-watt mobile, if that was set to 1 watt, this becomes the overriding parameter, and the radio can never transmit more than 1 watt, even though it's capable of 10 watts. And the third rule is they are bounded by 5 dB steps. So they don't step instantly, but they do step in 5 dB steps, and there is some hysteresis in there as well. Now, I mentioned rotated vector. You saw the constellation diagram and the vector diagram whizzing around like a ball of string. But what I find the most useful one is the rotated vector. So we actually take 8 of those all 8 timing points, all 8 constellation points, and we mathematically rotate them into one. Now, as you go in and out or left to right, we're looking at amplitude. And as you go around the circle or the arc, we're looking at phase. So here's 3 examples, and these are all real radios. So the one on the left, you saw that before. That is because of the way the burst timing is done. So they're ramping up very close and ramping down very close to the limits and what they're allowed. So you're seeing some amplitude features, shall we say. On this one, it may be difficult to see. There's most of the signal is sitting here in the middle, but it looks like almost like 4 straight lines next to each other. But you'll also see there are some more points up here. So there's some phase noise issues, or phase issues with the radio, and a little bit of carrier leak. And this one over here, there isn't really much phase noise, but you'll see again those 4 clearly defined points. So again, we have some carrier leak issues here. And this one actually here, I measured on a local police airwave base station somewhere near to where I live. So I monitored this, and it was actually a base station that was on the edge of being out of specification. And then when annual maintenance came around, it suddenly got better. They changed the base radio. Didn't really impact the radio users much, so they didn't complain. But it was actually, out of spec and didn't get picked up until the yearly maintenance. For DMR receivers, we can have a number of standard test patterns that are available. Okay, and you can select those on the test set. A common one to use is what's called the 1031 pattern. It's actually a 1.031 kilohertz tone, but in all respects, it may as well be a 1 kilohertz tone. So we can hear coming from the radio receiver. We have a calibration tone, and we have what's called a 511 pattern, which is a pseudo-random PN9 sequence, sometimes called a 0.153 pattern. There's probably about another 10 patterns One of those that we use sometimes is called stored speech. And if you listen to this, it will actually play speech out. Originally designed for P25, we put this into the P25 standard, and it was liked so much we got asked to put it or include it into the DMR standard. So if you listen to this on a radio, you hear things like, he took the crosstown bus. Don't throw trash on the street. His shoes were black and brown. So you get all these different American accents and different keywords are being used. And you'll realize what they're saying, breaking it up, the sentences are saying, the white guy crossed the street and went into the shopping mall. So you actually see these little messages. They're all sub messages that make up maybe the types of phrases that police or paramedics or fire people would use. So stored speech can be quite good to listen to a human signal, shall we say. And then another important one, this standard OBT sync, nice fancy name there. But basically, if you have a radio that is configured to run on a DMR repeater channel, it will not transmit unless it sees a repeater. So by using this test signal, we can fool it into thinking we're a repeater, and it will actually key up its transmitter. So if we're doing receiver tests, sometimes you can see something on the display of the radio if you have a key sequence you can press. Excuse me. But typically you might use manufacturer software. So here's an example. I'm using the Motorola tuner software for my DP3601 that I've got here. It tells me to set the frequency to 136.025 and the test pattern. I'm at a high level, minus 80 dBm into the radio, and I get 0% bit error rate. That's what I would expect. If I go down to more like the sensitivity level, so exactly the same measurements, but now I'm using a minus 120 dBm into the radio, I'm now measuring 2.62% bit error rate. And you're allowed 5%. So that's okay. You'll notice some little square plus or minus signs on some of these measurements. Any power measurement you see here will have a plus or minus next to it because I've added cable loss. Always remember to add cable loss for your test cable. Otherwise, if I think I'm putting out minus 120 and I have no cable loss compensation, the radio is probably receiving minus 121 dBm, and that could then fail the radio. So always be careful with cable loss. Okay, if you don't have tuner software, you don't have an internal bit error rate meter displayed on the radio, there is another way you can do it. You can use the 1031 pattern, listen for the 1 kilohertz tone, and I'm doing that exactly here. And you'll see in a moment, I'm going to reduce the level, and you hear it break up. Okay. So that's giving me an approximation of the sensitivity level of the radio. When it breaks up, typically it's around about that 5% bit error rate region. If it squelches, quite often it's because it's gone way above 5%. Okay, so it could be squelched on the RSSI value, the received signal level, or it's squelched because of the bit error rate is so bad. Okay. For TETRA receivers, we can do different modes of operation. Oops. So we have base station T1, which is a test mode for the base stations that's written into the ETSI standard. We have a mobile T1 test mode. There's also a mobile, what's called TD loopback test mode. That is not mandatory, that is optional. So that has only been supported by Airbus because of the history going back through to Nokia and how they did the same effective measurement on the GSM and 3G phones. And then direct mode, we can do something fairly basic. So we have all the capabilities for different receivers. For mobiles, typically we would use what's called a T1 Type 1, which is a 7.2 kilobit traffic channel. There are others available to you, but that is the one that most people will use. If the radio supports RF loopback, you can loop that back into the test set and actually measure the bit error rate on on the test set. Otherwise, the radio may measure the bit error rate on the screen, or you might use the manufacturer's tuner software, something equivalent to the Moto Turbo tuner software you saw for the DMR radio, or you might have the luxury of having engineering software. So in that case, you can run a program like this and look at the bit error rate at different power levels. Okay, so you can see here the power level is fairly well matching what I'm putting out of the test set, and I'm getting bit error rate measurements directly here. Okay. Again, if you don't have a way to measure that bit error rate, again, you can use a 1 kilohertz test tone and do what I showed you with DMR, where you lower the level until the signal breaks up. For TETRA MS, again, you could use TT loopback if it was Airbus radios, and then you press, once the radio registers, you press *#5667#. I don't think that's secret anymore, which actually stands for loop. 5667 is loop if you look on the keyboard, so we're looping back. You confirm that test mode on the test set, otherwise the radio will go back into normal operational mode for security reasons. And then the radio decodes the data, good or bad. If it's a sensitivity, there will be some bad decode. Whatever it's received, it transmits back at high power. And again, we can do those bit error rate measurements directly on the radio test set. For base station, it's broadly similar. Again, we typically use a 7.2 kilobit traffic channel, voice channel, as our test signal. And the base radio, again, will typically measure the bit error rate using manufacturer's software. Okay, but we need now timing synchronization, because the bit error rate meter needs to know when the frame or multi-frame of the radio system is happening. So some manufacturers use what we call an off-air signal, so they have the transmitter running. We time synchronize to that to transmit back into the receiver for bit error rate. Airbus would be one example. Or we use pulse sync. So we actually have a pulse sync, TTL pulse sync coming from the base radio, and we use that for timing synchronization to transmit back to the receiver. Motorola is an example there. That's what the software gives us back from the base radio when we're hooked in service mode. So this is two examples. Anyone that's testing base stations will probably know which manufacturers these are because of the format. But it gives you an idea of the type of measurements that you get from the base radios. For direct mode, there is no real effective method. So all you can do is key the base station, i.e. the test set, key the golden radio, the test set, at a low power level, and see if the radio receives that call or that message on its receiver. If it receives it, it's sensitive enough. If it doesn't receive it, it's lost sensitivity. So you have an approximation again of its sensitivity. Okay. There's a couple of videos I'm not going to go through now because of time, but you will have these when we send out the presentation, or put it up on the web if people want these. If you can't find them, then obviously drop me an email. I'll get them to you. And I have some DMR ones as well. So for DMR, we can use really any of the three test sets. They do broadly similar things. Bear in mind that I haven't talked about repeater testing. That will be a separate topic, a separate session. But 3550R does not support DMR repeater tests. 8800, the portable unit, and 3920B, the bench unit, they both support repeaters. 3920B supports ETSI compliant TETRA tests. That we were the test equipment manufacturer that wrote virtually all of the test section of the ETSI standard for this. We've also done that for DMR and P25. Okay, the portable test sets 8800, SX, 3550R, they only support TETRA base station modes, not the modes for the mobiles and portables. We also have auto test capability for many of the radios for either automatic testing or automatic realignment. Again, that's a separate topic area, not for today. And as it flashed up at the bottom, I always tell people, do not forget to add your cable loss compensation. It affects your transmit power, so you can fail a good radio or tune a bad radio. And it affects your receiver sensitivity. Again, you could fail a good radio, or conversely, you could pass a bad radio. So always check you have included cable compensation. And if you are using any of the analog test sets, and in here you'll actually see test sets from the historical Viavi family as well. I think probably at least 3 of these are ours. Just be very cautious if you're trying to test or tune digital radios. So thank you. Now I'll hand it back to myself and the other guys on the call, Francesco and Hamish, and we'll have a few minutes on the question and answer session. And thank you for your time.
Thank you, Barry, for your in-depth presentation. We have a few questions that we have received from our audience, and some are on TETRA, some are on DMR. Will you add TETRA testing on 8800 and 3550 for the portable and mobiles? This is one question.
So the question is, do we have test capability for the portables and mobiles? Not yes. At this time. Originally, we had it on the 3920B, which is what I will say almost all of the manufacturers have used. It's been the de facto industry standard, still is, and they've used it for R&D, they've used it for production, they've used it for commissioning base stations, they've used it in service workshops and field measurements. So when we brought out the 8800 and 3550s, the portable units, they did not have the TETRA capability at start. They had nothing on TETRA. What the market was demanding was a smaller, lighter, battery portable unit for TETRA. And the main cry for help, shall we say, from the industry was the portability and the size for the base station guys. You know, you're not going out into the field and sitting on top of a hill testing portables and mobiles. You are hiking up hills and mountains. Because your truck doesn't go to the top. You may be hiking up there or even going in a helicopter to test a base station. So we focused on that. The customers demanded it. That's what we did. We supported the customers that had the biggest requirement, which was the size and portability for the base station testing. So yes, we have base station testing, and at this time we do not have portables and mobiles.
Thank you, Barry. Then I have one question on DMR that I want to raise. Why can't I just use my analog test set to tune my DMR radios? It's calibrated and good enough for all my analog radios.
Yeah. Okay. So you can take. You know, I'm a Marconi guy. My history started here as a Marconi guy. I could take a Marconi 2945B, which is one of the best analog test sets that's been out there. Of course, I would say that. I could have got that back this morning from the calibration house. Okay, so I have a full calibration certificate. No problem for my analog radios. But if I use it to tune my digital radios, remember I'm using CW, so unmodulated, and I'm using FM modulated signals for tuning. And this is for the digital tuning as well. If I use the analog test set for my digital tuning, I may get a good radio. Equally, I may get a bad radio or a very bad radio, but I don't know. I know it works in FM. I don't know how it's working in digital. I believe I've tuned it very, very well. How do you find out? Well, you have to put it on a digital test set in DMR mode and then measure it. And you'll find, and I've seen this with production lines. One manufacturer, he had about 100 radio test sets on his production lines. His radios, the FSK era, where you see that those 4 nice straight lines, vertical lines, were quite fuzzy. The international limit is 5%. His radios were somewhere between 4.5% and 9.5%. 90% of his radios were illegal. They were out of international specification. He was shipping them to customers, commercial and military. They were saying, these radios are rubbish. FM, fantastic. I put them into this fancy digital mode, they don't work. Then they were switching back to FM, and a lot of the radios were coming back to the manufacturer. They were checking them, no fault found. As soon as I showed them just random samples of their radios on our test set, they very quickly realized they had a major problem, and they very quickly realized they needed to displace most of those radios, radio test sets, with the modern digital ones. So that's one example, but if you use an analog test set, you're going to compromise your radios. I'll almost guarantee it 100%. And what is worse, the manufacturers will give them to you, usually at very good performance. You may then retune them after 1 year on your analog test set, and you've now degraded the network. And we've seen this over and over again. The network size, effectively the cell size, will shrink because of the transmitted signal quality. It has nothing to do with power, has nothing to do with the receiver sensitivity. Okay, if they are set good, which you can do, you can check receiver sensitivity in analog mode. You can check the output power in analog or digital mode. But if the transmit quality is poor, that will seriously impact your network. We've seen networks shrink by over 50% size in terms of the radius. Real networks. Retune the radios, and remember, it could be the base station, it could be the repeater, it's DMR, or it could be a portable or mobile at the other end. Okay, remember there are 2 radios in any radio link. So both transmitters have to be good quality. So don't just think of the portables and mobiles, think of the repeaters and base stations as well.
Okay, thank you, Barry, for your explanation. I think we have no time for additional questions. We have received a lot of them. We will answer directly to the people that have raised the question. Now, this presentation has been recorded and will be sent to you in 48 hours. I would like to thank you all for attending this webinar, and I would like to thank you also, Barry, for giving his time in illustrating this topic. We are going to have additional webinars, and we will keep you posted with all this. Thank you very much, and have a good day.
Thank you, everyone.